Yes.
You got to show me before you leave how to turn that thing.
I guess I'll get started. My name is Doug Dunham, and my website is listed there, and I have my talk on my website in case you missed anything. You can go back and look at it. It's in PDF format. And I should say that I have been fascinated by the hyperbolic art of M.C. Escher, particularly the circle limit patterns, for over 30 years now, and created the first program about 30 years ago, which is about 20 years after Escher created his hyperbolic his circle limit patterns. In these patterns here, some of the bottoms may be cut off, but I think you can get the idea by seeing the tops of the patterns. That's Escher's circle limit 3. This is a quick outline of what I'll talk about, short history, and then I'll talk about a repeating hyperbolic pattern algorithm based on regular tessellations, which we've seen examples of those throughout the talks. And then I'll talk briefly about a repeating pattern algorithm based on non-regular tessellations, which needs the future work. And the history can be broken down into hyperbolic pattern history can be broken down into pre-Escher, Escher's patterns, and then post-Escher I would say would be the computer-generated hyperbolic patterns. And a number of people have contributed there. I was not the first one, but I think my students and I were the first one that reproduced Escher's circle limit patterns using computer-generated techniques. So, pre-Escher, we've seen these hyperbolic patterns for over 100 years now that have been published. And this is a famous pattern in a paper by Coxeter in 1957, sent it to Escher. Escher saw this pattern and said it gave him quite a shock, those are Escher's words, because in an instant it showed him how to make circle limit patterns. He was aware of point limit, he knew how to make point limit patterns, and he knew how to make line limit patterns. But this showed him how to make circle limit patterns. And I think you can see just by looking at this pattern, how he came up with this first circle limit pattern. Essentially, just by changing the colors of half of the black and white triangles to the other color, and made kite shapes which could then be modified into fish. And this is his circle limit pattern. Incidentally, how do we know they're fish? Because some people see birds. Actually, the only reason we know is because Escher said we're fish. This is his least well-known circle limit 2 pattern. And here is his most famous circle limit pattern, circle limit 3. And then this is the only pattern, this pattern of angels and devils, that he realized in each of the 3 classical geometries: spherical, Euclidean, and hyperbolic. So that's the history. How do we generate these patterns? Well, following Escher, we use the Poincare disk model of hyperbolic geometry. Incidentally, I should say that the concept of hyperbolic geometry was something that Escher was not comfortable with. He just saw these as Euclidean constructions, and the use of the word model in talking about hyperbolic geometry means that we use Euclidean constructions and give them hyperbolic interpretations. And these, in the disk model, the points are the interior points of the disk. The lines of this, the hyperbolic lines of this model, are orthogonal circular arcs that are orthogonal to the disk, together with diameters in special cases. And you can see on the bottom right there, there's a point where the white fish nose meets, and that is a point that's not on the the vertical diameter, and there are two hyperbolic lines that go through it, so it's definitely not Euclidean geometry, it's hyperbolic geometry. And in order to create a pattern, there's two basic steps. One is to create your motif, your basic subpattern, and the interesting part to me is generating the entire pattern from the motif. And here's an example of the motif for Escher's circle and one. I didn't say, but the black and white fish are different, and so you need, but they do have reflective symmetry across the natural line, so you do need half of each one in order to make fundamental region or basic subpattern of the motif. Now, Escher's circle limit patterns were all based, and actually many of his Euclidean patterns, and I think all of his circular patterns are based on regular tessellations. This concept applies to all three of those classical geometries. Tessellation is regular. It's composed of p-sided polygons needing q in each vertex, and the product of p minus 2 times q minus 2 determines whether it's hyperbolic, Euclidean, or spherical. And this is an example here, and it shows that circle limit 1 was based on the regular tessellation 6,4. Circle limit 4 is also based on this tessellation. Circle limits 2 and 3 are based on the 8,3 tessellation. Now, this is a table of regular tessellations, and the stars represent hyperbolic tessellations, the squares represent Euclidean tessellations, 3 familiar Euclidean tessellations, and the circles represent spherical tessellations, essentially the Platonic tessellations. You can see that there are a lot more hyperbolic tessellations, but the ones that work best are the ones that are near the bottom or the left or the bottom half. And the title of this talk was Special Cases. In fact, I think that was part of the theme of the conference, and that's what I want to focus on here. The special cases here are when p equals 2, incidentally the values of p are along the bottom there. The values of p equals 3 or q equals 3, that is the edges. Those are the ones that present the special cases to the algorithm that I would explain that when we get to it. And in order to replicate the pattern, what I did is I simplified things. Rather than using a single motif, I used all the copies of the motif that were arranged around the center of the bounding circle, and I call this the so-called polygon pattern. This facilitates the replication process, means you have fewer transformations to apply, and so forth. And this concept of aggregating the motifs around a point, you see that in Euclidean repeating patterns too, where it's called a translation limit. And then you can see for circle limit 1, this is a so-called polygon pattern. And these regular p-sided polygons, or polygons for short, come in layers. And the first layer is just the center polygon, and then each layer beyond that is defined in terms of the previous layer as all the polygons you haven't counted yet that touch the previous layer, either by sharing an edge or by sharing a vertex. And we'll have to make a distinction about those two cases. They play a role in the replication algorithm. And of course, theoretically, in hyperbolic geometry, as in Euclidean geometry, it's an infinite number of copies of motif or polygon, infinite number of layers, but we can only see a finite number of them. And in the hyperbolic case, it's nice because they get smaller toward the edge, and after a while, they just blur into nothingness and you don't have to do it anymore. So this is the 6-4 tessellation that we saw before, and you can see the I can use the pointer here. You can see that this is the central polygon. This is the first layer. The second layer includes this polygon, this polygon, this polygon, this polygon, this polygon, and so forth. This shows 3 layers. And you can see that this polygon is attached to the previous layer by an edge, but this one just by a vertex. And a polygon that is only attached by an edge to the previous layer, we say has minimal exposure to the outside because since it already shares one edge with the inside, it shares one fewer edge with the outside. So it's 1 of 3 edges on the outside there. But for a polygon that shares only a vertex, we say that this has a maximal exposure to the outside. There's 4 edges that are exposed to the next layer out. So that concept of exposure is something that I'll talk about right now. And I've explained that in the pseudocode below, just to save space, I call the minimal and maximal exposure min exp and max exp. And the replication algorithm that we and I and my students have developed consists of 2 parts. One is a top-level driver routine, and it's simply called replicate. And the second routine, actually in the code, it's called, the code we actually use is called recursive replicate, but again, in order to save time, I abbreviate. And the recursive replication routine is the one that essentially does the work after it gets launched by the first one. And in order to create repeating patterns based on polygons, it's necessary to know how to transform across each of the edges of the polygon. And those transformations are stored, we store those in an array called the edge transformations. And I don't know if you can see all of this. So this is the top level, and we iterate over each vertex. I consider iterating over the vertices rather than the edges because I transform around each vertex. And actually, we can see all the code here. The rest is just ending what we see above. And you can see that there's another routine called draw polygon that just draws a polygon, a polygon pattern actually, based on the polygon pattern in the motif and which transformation applies. And initially, just the identity is needed for the center of the polygon pattern. And so what I need to do is I need to iterate around each vertex, and so I need to apply transformations. I need to know what starting transformations to apply, and what they do, and what they are is given by. What they are is given. Just one thing. What they are is given by this, just by this formula here, and then the new exposure. Depends on whether it's the first iteration or not. If it's the first iteration, then that's going to share an edge, and there's going to be minimal exposure. The next iterations only share vertices, and so they're going to have maximum exposure. And then that's passed on recursively to this replication. And then as I iterate around the vertex, I keep having to add to the transformation that I use. This -1 essentially means I add one more transformation, and the minus means for some reason we have to go and clockwise or backward. And then this is how we add the transformation. Essentially, it's if the argument is 0, if the shift value is 0, then we can use the transformation we already have. Otherwise, we have to compute it, and show the pictures and show the rest of that. That's the transformation multiplication that simply using the calculation for where the new starting point should be, it adds it to the current transformation. And this transformation multiplication, we use matrices, and so it multiplies the matrices. Also multiplies the orientation, because we do have to take into account possible orientation. Well, I mean, you saw Escher's circle in a 1 or reflections, so our program does take that into account. And then the positions to start with, it's all just a set. And then this is the recursive replication. It has the same structure in that there's an outer structure that iterates over each of the edges, exposed edges, or essentially their corresponding vertices, and then an inner loop that iterates over about each vertex, about each of those vertices. And you have to calculate the number of vertices to do depends on the exposure, and the number of polygons to do about each vertex also depends on, let's see, that depends on whether you're doing it for the first iteration or a later iteration. And this formula, I mean, this algorithm here, well, I'll just go ahead. This algorithm works for if P is greater than 3 and Q is greater than 3. If either P is equal to 3 or Q equals 3, then the basic algorithm works the same, but we have to use different values of these arguments. And these are the special cases. So the algorithm then becomes more complicated, where we have to take these special cases into account. And if P is equal to 3, in replicate, nothing changes. In the recursive routine, though, then there are these changes that are listed here. And at the bottom, the rest is cut off, but in both replicate and recursive replicate, in the inner loop, the last time that you do it, you simply draw the pattern. You don't generate another recursive replication. And the reason is when P is equal to 3, you have triangles. And one triangle, if it has minimal exposure, doesn't have any edges. It doesn't have to generate anything for the next layer. And so that's why there isn't any recursive call in that case. And then the case Q equals 3 doesn't have any special case like that, but it does have different values in these different arguments. And the one thing I forgot to say, an important thing in these algorithms, is that initially when I was designing these algorithms, our only output device was a pen plotter. And that has implications. Well, in order to draw a pattern, of course, you want to see all copies of the motif, but you don't want to draw them more than once. Or at least you don't want to draw them a lot of times, because if you do with a pen plotter, it cuts through the paper. And that happened. And so we were under a lot of pressure to make sure that we didn't mess up the computer center's plotter. And so the idea is not to duplicate the drawing of any motifs. For practical reasons, even after pen plotters, it turns out that if you have duplication, it grows exponentially with the number of layers. And so the idea is to come up with algorithms that draw each motif exactly once. And these algorithms, with these special cases, do. And here are some patterns. And these are patterns that we've seen before, actually, today, and probably saw yesterday and the day before, Escher patterns. And this one inspired me to make them. I think. Well, I started making more Escher patterns when Escher also created spherical versions. And he has this is a spherical version of this fish pattern. It's notebook drawing number 20. And each of those fish we saw above has, let's see, they have 5, well, this pattern has 5 fish meeting at dorsal fins. The Euclidean pattern has 4 fish meeting at dorsal fins, and the spherical pattern has 3 fish meeting at dorsal fins. Then, as I said, this is Escher's, the only pattern that Escher generated in each of the 3 classical geometries. And this is the first one he did in 1941, I believe. And it's based on the square 4-4 tessellation. This is a reproduction of sphere ball that he carved in 1942, I think. And it's based on 4-3 tessellation. And so I wanted to, and as I showed above, in circle in the 4, that's actually based on the, let's see, I have to look at, it was based on the 4-6 tessellation. I wanted to see what it would look like with a 5 tessellation, and this is the example here. This is a different heaven and hell pattern. And we saw this pattern of butterflies, I believe, earlier too. And this is an interesting pattern, not so much in the Euclidean case. It's easy to get a 3 coloring, as you can see there. In the hyperbolic case, and this is, I apologize for not having more special cases, more boundary cases, but this is the one example I have of a boundary case where Q is equal to 3. I have this exact same pattern with the 7 and 3 reversed, and I just neglected to include it in this slideshow. But as soon as you have 7 butterflies around the center, then the challenge of coloring becomes much more complicated. 7 is a prime number. You need at least 7 colors. And if I go back, in Escher's pattern, if you look closely, say around, let's see, around here, you have red and yellow butterflies alternating, and the colors of the circles on the wings are all the 3rd color that doesn't appear, which is blue. And the same is true for everywhere else in the pattern. And so I tried to adhere to that policy here. Now, if I've already used 7 colors, then I have to use an 8th color to get the circles on the wings to be a different color. And so the color for the central ones I used was white. And I actually, initially, before I had this high-end hardware, I actually colored in a sample of this by hand. It was very laborious, and until I realized that each of these groups of butterflies came in circles. You can see a circle of white butterflies, and the circle of white butterflies surrounds a group of 7 other butterflies of the other color. And that's true of all of the colors. So you can see in circles here, there's a circle of red butterflies, a circle of green butterflies, and so forth. One of the hardest patterns I had to create, but also one of the most satisfying. Now, for non-regular tessellations, the first thing I considered was p-sided polygons, and they're Q1, Q2, up to QP copies of the polygon around the respective vertices. And this and such a tessellation, or such a polygon, can form a hyperbolic tessellation, provided this rule is true here. This is a generalization of the p minus 2 times q minus 2 being greater than 4. And the idea here is that the interior angle of the ith vertex is q sub I. It's 2 pi by q sub I, excuse me. And this tessellation, I just denote p semicolon. And the algorithm, the pattern algorithm that I use for this is based on the previous one, in that it has it has a driver version and it has a recursive version. And the driver version calls the recursive version that does all the work. Now, this is a boundary, again, this is a boundary case. And in this particular case, if either p equals 3 or any of the q's equal 3, it's possible that both of them could be equal to 3, then there are duplications, multiple copies overall. So that's one thing that I hope to fix by this conference, but it seems to be a hard problem. And this is an example of such a tessellation. So quadrilaterals with 6, 3, 4, and 6 copies of it around each vertex. And the top level driver is even simpler than before, because the top level driver here is, unlike the previous one, which has an entire p-gon pattern in the center, just essentially creates its version of the p-gon, has to create its version of the p-gon pattern around the center, which essentially just iterates around the first vertex. So it just iterates around the first vertex, copying the motif as it goes around. And then the replication has the same structure. The arguments there are somewhat more complicated, but essentially it does have the same structure. It calculates the same kinds of things. And you can see some of the same functions have been reused. And this is an example, an example that we've seen before of a pattern. So Escher's 3-element pattern. I think it's his drawing number 85, drawing number 85. The 3 elements are the yellow bats for the air, the blue lizards for the ground, and the red fish for the sea. And here, this is a pattern that I could not draw using the original regular polygon, regular tessellation pattern, because there are different numbers of each animal that meet nose to nose. And then this is another version here. In this version, there are 3 bats, 5 fish, and 4 fish, 5 lizards eating nose to nose. And then this is a different combination of those. But I find it interesting that people always pick the same Escher patterns to base their examples of Escher's symmetries on. And the future work is to fix the problem with the non-regular tessellation in the special cases. And it is possible that some or even all of the vertices of the fundamental polygon could lie on the bounding circle in the general case, even in the special case. Well, in the regular case, then they either all have to lie on the bounding circle or not. And that's all of that. That's the end. Yes.
Yesterday, Rutgers was talking about symbols where tessellation is represented by how many figures we want to meet in the sequence. For instance, we could start with sequence 4, 6, 5, and it means I want to have a vertex where 4 figures meet and 6 where it doesn't say that we are what kind of regular polygon we use. And there are also some other symbols you use. And on the web, it's also, there are at least 2 different symbols basically.
Oh, yes.
Is there a good program or algorithm that kind of takes symbol of one kind and gives you possible symbols of the other kind, plus as you with the generation of the group that actually does that?
Yes. Well, yeah. What I'm thinking of is there's a new book, Symmetry. It was by Chaim Goodman Strauss and Conway and Gruber, I think. Anyway, they discuss these different notations, like the orbital notation and so forth.
There's no tricking action.
I think they talk a little bit about generators and relations. Yeah, the generators are, in my case, are simple. They're just the edge transformations. The relations are simple too. Let's just work. Let's consider a single edge that can go onto itself. In other words, a single edge. I can reflect across it. That's orientation reversing. Or I can rotate about its midpoint. I can use either one. Yeah.
And which programming language do you use?
What program? This is in very old C. I currently have students working